All right. Well, welcome everybody. It is a real pleasure for me to be the chair of this session today. The speaker today is a very dear friend and a very important figure in all my professional career, Jim Berger. And well, I don't think Jim needs a lot of introduction, but just in case you want to know something about him, he is the arts and science professor of statistics at Duke University, and he has made so many seminal contributions in the development of Bayesian statistics that it would take hours to essentially go through all of them. You can read some of that in this slide. I can find very few other people who would be more appropriate to give this lecture in the honor of Bruno de Finetti. Joining Jim, we will have today two discussants. One is Luis Raul Pericchi, who is also somebody who has done a lot of important contributions to the development of Bayesian methodology, and from University of Puerto Rico. And then we have Igor Pruenster from Bocconi University. Well, without any further ado, I'll leave you with Jim Berger, who will have about 55 minutes to give his presentation, followed by the two discussants, and then we will open the floor for questions. Please write your questions in the question and answer window in the chat. All yours, Jim.
Okay. Now, wait a minute. It was there a minute ago, but then it disappeared. Let me try again. Okay. And view. All right, there we go. It's showing up?
Yes.
Okay, great. Okay, I'm delighted to be the De Finetti lecture. My thanks to the committee for choosing me to give this. I'm also delighted to have Luis and Igor as discussants. Luis actually made me give this lecture. I was going to give a different lecture last year, but then we started talking about this in the interim. He said, no, you have to talk about that. And so I went, okay. I also realized that it actually ties in kind of quite closely with much of what De Finetti did. He started out as an actuary, and as we all know, kind of actuarial reasoning involves both frequentist and Bayesian reasoning quite extensively. He became known as a great subjectivist, partly because he strongly opposed the frequentist definition of probability as the foundation for probability, and he thought a subjective foundation based on betting was much more mathematically sound. He also developed surprising representation theorems showing how simple assumptions such as exchangeability implied subjective Bayesian modeling. Now, when you look at these arguments, these things like the representation theorems used frequentist arguments all the time. They're based on frequentist arguments. It's curious that he's using frequentist arguments all the time to end up saying you must be a subjectivist, but that's what he did. The big, I think, difference between his frequentist arguments and what the common ones are is that he focused on long sequences of observables. To him, observables were everything, and he would consider long sequences of observables. And that's actually going to be the main focus of what I talk about today, is that when you properly try to define what a frequentist is, you need to focus on long sequences of observables. I'm going to skip De Finetti's theorem because I don't have enough time and everybody knows it. All right, so there's Bayesian statisticians today, and if you ask anybody who's a non-Bayesian what they are, they probably say they're a frequentist. But they mean very, very many different things by that, and part of what I'll try to do today is describe what I think are the common frequentists and what they mean. Some caveats. I.J. Good in 1963 identified over 46,000 potential types of Bayesians, and there may well be as many or more potential types of frequentists. I'm only going to talk about 4 today, really only 3. I will use the word frequentist to refer to doing some type of long-run average or some type of long-run frequency. Many people use the word frequentist to refer to what are essentially Fisherian concepts that do not involve a long-run average, and I'm not addressing that kind of so-called frequentism. There's almost no chance that what I say today is original, at least in terms of the formulations of the frequentist principles, but I think there's probably something original in some of the later computations. Okay, so here they are, what I think viewed as the 4 most common types of frequentism. And these are in roughly descending order of what I would call quality. You know, the first is the best. Conditional frequentist principle is not something I'm going to talk about today, partly because frequentist conditioning gets very close to objective Bayesianism. In some sense, if there is an objective reality out there, approaching that objective reality either as a conditional frequentist or as an objective Bayesian, it's kind of like 2 sides of the same coin. They end up in the same spot. I've given many talks about this in the past. I'm not going to do that today. It's just too big a subject. What I really want to focus on today is this first thing called the empirical frequentist principle, but I'll also talk about the procedural frequentist principle and computationally frequentist principle. And rather than talk about them on this slide, we'll talk about them in depth on subsequent slides. So let me leap in on that. Okay, first of all, empirical frequentists. So this is what I think all frequentists should be, and also sort of what Bayesian should be. And partly what I'll be doing today is try to show that a large number of frequentist procedures don't satisfy this, and they should. They satisfy a different version of frequentism, which is not as palatable. Okay, so here it is. In repeated practical use of a statistical procedure, the long run. Okay, the average actual accuracy achieved should not be less than, and ideally should equal, the long run average reported accuracy, in the sense that the difference of the 2 should go to 0. The long run average reported accuracy is what you say on average in the long run as to your accuracy. The long run actual accuracy is what actually happens. So what you say in the long run should average out to what actually happens in the long run. What you say should be what you get. That's the empirical frequentist principle. 2 points: it emphasizes considering real observables. It emphasizes thinking about a sequence of real experiments, real data, and thinking about what will happen. Again, this was the focus of De Finetti. This is the kind of argument he would make all the time. And it focuses on having good behavior over the sequence of real observables. Again, as De Finetti did. I mean, I almost thought of, maybe I should call this the De Finetti frequentist principle, but then I thought he'd probably roll over at his grave, so I refrained from doing that. I'm not stating a formal definition of this in general, because there's many variants. I'll illustrate this on 3 examples: confidence intervals, unbiasedness, and empirical Bayes. Okay, so I'll spend a fair amount of time on confidence intervals because this is the clearest description of the setup, and in some sense, the clearest conclusion. So we have a sequence of real problems, E1, E2, and so forth. Each one is a separate experiment yielding data xi that arises probabilistically from a distribution having unknown parameter theta I. And these can be completely different experiments. They don't have to be exchangeable. They don't have to be anything. Let me just pause here because people who are used to the textbook definition of frequentism think of frequentism as meaning something completely different. The textbook definition is this thing here. You pick an experiment like E1. You pick a value of theta, like theta equals 10. And now you repeatedly generate imaginary data from that fixed E1 and from that fixed theta equals 10. And then you study how the procedure performs as you repeat generating this imaginary data. There's nothing in that description of sort of the textbook frequentism which bears any relationship to reality at all. It's just all an imaginary thought experiment. Here, we're talking about reality. we're facing a sequence of real problems, real experiments, real data, all differing, and we're applying a procedure to them and trying to study what happens. Okay, so here we're doing confidence intervals. So we're going to have a confidence interval for each theta I with stated confidence 1 minus alpha I of xi. And again, disabuse yourself of any notion of what I mean by confidence here. I don't mean anything. It could be frequentist, it could be Bayesian, it could be likelihood, it could be anything. This principle doesn't care what these things are. It just says how they should behave. So you are going to produce confidence intervals and some measure of confidence. And then let's imagine that one eventually learns whether or not the confidence interval contains theta I. In some cases, this is very realistic. Let's say we're targeting stock prices in the future, or we're targeting weather forecasts the next day. Eventually, we learn what the truth is, and we can actually say how accurate we were. Now, the empirical frequentist principle, a very natural formulation of it in this context, is to say, as the number of experiments, capital N, goes to infinity, each time we're reporting an accuracy, a coverage of 1 minus alpha I. So what we say on average is just the average of those numbers. That's the average accuracy we're reporting. The actual accuracy is simply the number of times the confidence intervals contained the unknown parameter divided by n. So the empirical frequentist principle says this difference in the limit should be 0. Sometimes it's viewed to be acceptable to be conservative, in which place you could have a less than or equal to here, but I'm not going to talk about that. Now again, when we look at things like this, we're used to thinking, okay, what does this mean probabilistically, mathematically? It doesn't mean anything. It's just a statement that about these reports and what happens. All sorts of things could be random here. Usually the data xi are viewed as random, with the joint distribution specified by the experiments given the thetas. But sometimes the theta i's will also be random, or there could even be other weird combinations. It's sort of notions of probability don't come into the statement of this condition. It's just a condition that could apply to many different scenarios. It's interesting that Neyman himself often tried to point out that he never explicitly stated the empirical frequentist principle, but he often tried to point out that frequentism applied to a series of different problems. It's that the textbook thing of just fixing one problem and repeatedly generating imaginary data is not necessary. So he himself, even though I don't think he ever explicitly formulated it, was sort of a believer in the empirical frequentist principle. Curiously, the textbook version of confidence intervals does satisfy this. Let's remember what that textbook definition is. Now we'll fix an experiment like E1, and we'll fix theta I, and then we'll randomly generate data, and we'll find out how often the confidence interval for this randomly generated data contains the true theta. So that's this coverage. And let's assume that's 1 minus alpha I, that is constant for all theta I, which is the ideal textbook case. Okay, now letting 1 c theta be the indicator function on the set C, 1 of theta is in C and 0 otherwise, we can rewrite our empirical frequentist principle, which was this: the average of what you say minus the accuracy you achieve. We can take the n outside, the summation sign. Well, I guess it is outside here anyway. What am I doing? Well, I'm just putting I'm taking the summation out and the n out. And what I'm left inside with is the 1 minus alpha I. And then the number of times Ci contains theta is just the sum of these indicator functions. So I'm just replacing that number by the mathematical quantity of the indicator function. Okay, and so the empirical frequentist principle says that this thing should go to 0. Now, a different way of writing the coverage probability, here I wrote it in terms of the probability of containing theta I, but you can also write it as the expectation of that indicator function. That's easy to show that. Therefore, if we look at this quantity inside the brackets, I've labeled it yi, 1 minus alpha I minus the indicator function. It's a zero mean random variable because the expectation of the indicator is equal to 1 minus alpha I. And clearly the variance is bounded by 1. This number can never be bigger than or less than 1 or minus 1. So we have a sum here of zero mean random variables with variance bounded by 1. So the law of large numbers applies and concludes that the limit's indeed 0, with essentially no assumptions. The EI do not have to be problems of the same type. The alpha I do not have to be the same. The theta I need have no relationships. It's just always true that this limit will converge to 0. Now, I'm not saying that textbook confidence intervals are a good thing necessarily. In some situations, they're very bad, but they do satisfy the empirical frequentist principle. Unbiasedness. We have a sequence of experiments EI with different theta I, and we're going to be using unbiased estimates theta I hat, which simply means that the expected value of theta I hat given theta I equals theta I. So if the theta I were to become known, the differences would then be mean 0 random variables, and one could observe that the average differences converge to 0 under mild conditions. So again, unbiasedness is an empirical frequentist property. I'm not particularly a fan of unbiasedness at all. So again, I'm not saying that everything that satisfies an empirical frequentist property is useful, but at least it satisfies the strong frequentist property. Empirical Bayes, here's a case where the theta I are also assumed to be random. So the theta I, here probably the experiments EI are in some sense exchangeable, and the theta I's arise from, say, a normal distribution with some unknown mean invariance. And then the data I are typically from the same distribution with parameters theta I. And so the empirical frequentist principle would say you do an analysis by averaging over both the theta I and the xi. And that would be, if you did that, and if indeed the theta I did arise from this distribution, the empirical Bayes analysis would satisfy the empirical frequentist principle. All right, so let's talk about interfaces of this with Bayesianism. The empirical frequentist principle seems compelling to most. I mean, I like to think of computer programs that, in this case, imagine one created to compute a confidence interval. Many different people use the computer program. They specify the 1 minus alpha I they want, the experiment EI they conducted, and then the program returns the confidence set. Suppose it is discovered that over many uses, the average reported confidence was 0.9, while only 70% of the confidence intervals actually contained the true parameter. I would call that a very bad computer program. It's not producing what people think it should produce. Now, I think even Bayesians should accept the empirical frequentist principle. I mean, this might get me in a bit of trouble here, but what the heck? Nobody can throw tomatoes at me. Suppose the computer program were a subjective Bayesian program that does prior elicitation and produces Bayesian credible sets. Okay. I would claim something is very wrong if the reported confidence and repeated use of the program is 0.9 with actual coverage of only 70%. And if this were a badly prepared computer program, that could very easily happen. There's sort of, it seems fairly well known, at least in the folklore, that if all you say were to do would ask a user to specify a prior mean and a prior variance, and then you fit some distribution to it and use that to develop the credible interval, that could be kind of bad, because the trouble is that people, and I've witnessed this often myself, very often when you ask them to report a prior variance and you don't train them properly about how to do it, they will produce a prior variance that's much too small. In fact, the folklore says it's a factor of 3 too small. And I have lots of empirical evidence that that's actually true. People just think they know more than they do. And then when they produce a variance, they produce a too small variance. So if the computer program was set up to do that, i.e. was set up not to do a bad job of elicitation, then you would end up with prior distributions that are too concentrated, and that could easily lead to credible intervals that are too small, and you could have, and you could miss much more often than you think. So I think it's even Bayesians should think about this when they develop procedures. Okay, let's move on. I'm introducing the other types of frequentists because they are out there, and also because oops, I just lost my light. Oh well. Also because I'm interested in, I guess you can still see me. Also because I'm interested in studying when these less useful types of less reputable types of frequentism actually satisfy the empirical frequentist principle. And in particular, there's something called sequential endpoint testing that those of you who do clinical trials know about, and those of you who don't maybe have never seen. It's a procedural frequentist procedure. I actually think of it as rather terrifying, and I've in times past spent a lot of time trying to convince people doing clinical trials that they should not do sequential endpoint testing. And my reasoning was because it's easy to see it's completely counter to Bayesian logic. You know, telling them, sorry, you shouldn't do this because it's counter to Bayesian logic doesn't actually work very well in the real world, unfortunately. So one of my motivations for this was to study sequential endpoint testing and show that it's also bad from an empirical frequentist perspective, and hoping that would be more convincing to get people to stop using it. Anyway, procedural frequentist principle, it's just the textbook frequentism. You fix model, you fix unknown parameters, and you consider imaginary application of the procedure to imaginary data arising from the problem. And again, we'll go through a few examples of that. We've already talked about textbook confidence intervals. I don't have to repeat them. Consistency is an interesting situation. A procedure is consistent if it converges to the truth as the sample size n goes to infinity. Again, I'm not stating things precisely mathematically. This is a procedural frequentist principle in that it involves a fixed given problem, and you imagine a sequence of applications where the sample size is growing. So that's only procedural. And there is, in fact, no natural sense in which this is an empirical frequentist principle. I thought about it a bit and tried to come up with one, and I couldn't come up with anything reasonable to make it into an empirical frequentist principle. Type 1 error, is another classic, just like textbook confidence intervals. Type 1 error is a classic procedural principle. You're testing H0 versus H1 with a rejection region R. Having type 1 error, alpha is the probability of the rejection region given H0. And it's clearly a procedural frequentist procedure. You're talking about the property of a procedure for a given model. We will later see that this is not an empirical frequentist procedure. Okay, so here's sequential endpoint testing. Here's this thing that I'm kind of frightened of. A sequence of null and alternative hypotheses are presented and are to be tested sequentially. This is the first test, this is the second test, and so forth. The ordering in which you specify the test is important. And this is, like I said, this is usually, I have seen this arise primarily in clinical trials and in testing for drugs or treatments, things like that. So we'll use that as an illustration. We have a new drug. This alternative, we're testing whether a drug provides pain relief or not. The null is, it does not provide pain relief. The alternative, it does provide pain relief. The second thing is the same drug. Now we're testing blood pressure. The null hypothesis is it doesn't do anything to blood pressure. The alternative is it reduces blood pressure. And then we have a third test testing weight loss. The null, no weight loss. The alternative, the same drug, promotes weight loss. Okay, the same nominal type 1 error, like alpha equal 0.05, as is commonly done in clinical trials, is chosen for each hypothesis test. And then the sequential process, this is sequential endpoint testing, it's kind of curious. You conduct the first test, so you test for pain relief. And if you don't reject, if you cannot reject the null hypothesis, you just stop. You're done. You go home. The drug is you can't advertise the drug for anything. If the null hypothesis is rejected, you then are allowed to perform the second test. If you don't reject the second test, you have to stop, and all you can claim is the new drug provides pain relief. If you reject the second test, you're allowed to go on to the third test. If you accept the third test, if you don't reject in the third test, you can claim the drug provides pain relief and reduces blood pressure. If you reject all three tests, you can claim the drug provides pain relief, reduces blood pressure, and promotes weight loss. Now you can see why pharmaceuticals love this. They go through a trial, probably this is the primary endpoint, they're trying to prove this, but then they get all these bonus things that they get to advertise that the drug is good for. So it's a real big hit with pharmaceuticals, sequential endpoint testing. Okay, here is the procedural frequentist fact, which is really quite fascinating. You have to really sit down and work it out for yourself before you believe it. It says the probability that anything you've done is wrong, the probability that you've made one or more false rejections, no matter what sequence of hypotheses is true or false, is less than or equal to alpha. Now, what's funny here is that each of these tests was done at level alpha, equal 0.05, say. You've done three tests, say rejected them all, and you get to report that your probability of an error is only 0.05. Now, why is that surprising when you first see it? Because we're used to thinking of traditional multiple testing. And if we were to conduct, for sure, all three tests, and we wanted to have an error probability, an overall error probability of 0.05, would have to do something like use the Bonferroni correction for each of the individual tests. We couldn't, if we want 0.05 overall, we'd have to conduct each of these tests at 0.05 divided by 3, which is about 0.17. So we'd have to do these three tests at level 0.017. Okay. In sequential endpoint testing, however, not all the tests are conducted, and this is simply a true procedural frequentist fact. But we will see that this procedure does not satisfy the empirical frequentist principle. Now let me get on to the relationships to Bayesianism and why I don't like this procedure at all. First of all, I mean, since it involves this imaginary sequence of experiments, not a set of real observables, I don't think it's particularly compelling to Bayesians. The consistency example, I sort of believe that consistency is an interesting thing. I would be loath to use a procedure that was inconsistent. So even though it's only a procedural frequentist principle, I kind of think it's a good one. The procedural case for type 1 error is weaker, and we'll talk a lot about that later. And now let's talk about sequential endpoint testing. The following is just kind of a basic equation arising from probability. If I compute in a Bayesian way the posterior probability that of the alternative hypothesis, given the data, that the drug reduces blood pressure, given the data, that's got to be bigger than the posterior probability of the two things, that the drug reduces blood pressure or pain relief and blood pressure and so forth. I mean, this is just the way probability behaves. And in fact, if you try to model these things in a Bayesian way, these probabilities drop quite sharply. So Bayesian analysis of the sequential endpoint testing says your error is dropping sharply as you reject more and more hypotheses. No, sorry, your error, the probability that you're correct in rejecting these things is sharply dropping as you reject more and more of them. And that was just in sharp contrast to the procedural sequential endpoint testing, which says your error is alpha all the time. So again, I could never get, I mean, seems so obvious, but I could never get anyone to really accept that this was a reason to reject sequential endpoint testing. But I think it's a compelling reason to reject it. If I look at a drug and see it's been approved for pain relief as its primary endpoint and 2 other things as secondary and third endpoints, I don't believe it. Okay, how much time how are we doing? Oh, I guess I'm doing okay on time. I should, to be fair, also mention that objective Bayesians often utilize procedural frequentist properties to help choose their objective prior. In fact, it's the primary way of developing objective priors. An example is matching priors are priors that yield posterior credible sets for a parameter that have good frequentist coverage when viewed as a confidence procedure. I mean, you can take the Bayesian credible sets and view them in a frequentist light and say, how well do they do in terms of frequentist coverage? And matching priors are priors that yield good ones. I ran across a few months ago an astonishing illustration of this, which has gotten lost in the literature. I don't know why. It was done by John Hartigan in 1966, ages ago. And he showed that for any prior having full support, if you find the 100 1 minus alpha percent equal-tailed posterior credible interval. Now, what does that mean? That's not the HPD credible set. That's, I think, the much more reasonable credible set where you find the posterior distribution. If you want a 90% equal-tailed posterior credible set, you look at the posterior distribution and you just lop off the bottom 5% of the posterior and you lop off the top 5% of the posterior, and that interval between them is the 90% equal-tailed posterior credible interval. So Hartigan showed that if you use that all the time, it has the following rather astonishing procedural frequentist property. As the sample size n goes to infinity, so it's an asymptotic result, the frequentist coverage of the Bayesian credible sets is 1 minus alpha up to an error of order c over n for some constant c. Now, why do I say that's an astonishing result? If you go to the frequentist literature, all of the standard frequentist methods of deriving confidence intervals, things like the log odds method or the delta method, any of the simple textbook methods for asymptotically obtaining a frequentist confidence set of order 1 minus alpha, have an error of c over square root of n, a much larger error. I mean, having an asymptotic error of c over square root of n is easy and kind of doesn't mean much. People work really hard to get an asymptotic error of order c divided by n. I've seen 30-page proofs simply trying to get, for confidence sets, trying to get c over n. Hartigan showed that any Bayesian procedure gives you c over n if you use equal-tailed posterior intervals. It's astonishing. I mean, I don't know why we've lost that. It's one of the most astonishing Bayesian results I've ever seen. Anyway, that's just an aside. Lastly, computationally frequentist methods. So now these are just kind of weird. This is just statistical procedures should depend on quantities that involve some kind of frequentist average over the sample space. Here's a ridiculous example, but I didn't make it up. I got an email one day from a scientist who said, my colleagues are going to publish the following result, and I don't think it's right, but can you tell me whether it is or not? So they were doing a binomial, effectively they were doing a binomial experiment, success probability theta, sample size 20. They were testing theta equals 0.5 versus theta bigger than 0.5, so that large values of x define the tail area, right? Large values of x will correspond to theta bigger than 0.05. Curiously, the actual observation was 4, The p-value they computed, they're saying, okay, large values of x to find the tail area. So they computed the probability that x is greater than 4, given the null hypothesis, computed it to be 0.999, and said that p-value is so close to 1 that that's overwhelming frequentist evidence in favor of the null hypothesis. Now, I mean, this is nonsense, of course. 4 is kind of, observing 4 on 20 is evidence against both the null and the alternative. The null, it's slightly more evidence for the null than the alternative. In fact, a Bayesian analysis, I think, shows maybe it's 5 times as much more evidence for the null as the alternative, but it's certainly not proving that the null is true. So this is just a bad frequentist argument. They had used a p-value, thought of it as being a frequentist procedure, so they thought, okay, we did a good job. Now, one can do bad things using any statistical methodology, so I'm just emphasizing the point that just because one has done a frequentist average or a frequentist computation doesn't mean there's any validity at all to the conclusion. That brings us to p-values more generally, okay, because in general, the use of p-values is not nonsensical. So p-value in general is the probability of a test statistic being larger than the observed value under the null hypothesis. So it is a computationally frequentist principle. However, it does not follow any procedural frequentist principle. For instance, here's one thing you might say. Okay, let's consider the imaginary experiments of repeatedly drawing data x from the null hypothesis, computing the p-value, rejecting the null if the p-value is less than 0.05, and then reporting the p-value as the error probability. That's what, in effect, a lot of people subconsciously do. They report the p-value, but think of it as the error probability. And they only reject if the p is less than 0.05. So this is the procedure, this is the computational frequentist principle that many people follow. Well, the actual type 1 error is clearly 0.05. It's a 0.05 level test. That's the rejection region. If you average the reported p-values over this rejection region, you'll find that the average of the p-values over this rejection region and under the null hypothesis is 0.025. So the average, if you're thinking of them as the error, the average error that you're reporting is 0.025, whereas the actual error is 0.05. Curiously, if you simply multiply the p-value by 2, you can show that, and you report twice the p-value as the type 1 error, that's okay. That would be okay from the viewpoint of a procedural frequentist. But we will see that this rather badly fails to satisfy the empirical frequentist principle. So you can fix a p-value to make it a procedural principle by multiplying it by 2, but you can't really fix it to make it an empirical frequentist procedure. Okay, interfaces of this with Bayesianism. Well, I don't know. Let me skip this. I don't think much of it. We all know that p-values are interesting and useful. It's just that they're not interesting and useful in a frequentist way. They're interesting and useful in other ways. And that's I think the main point of what I'm saying. Okay, now I'm going to turn to hypothesis testing to try to illustrate these things more. And to keep things simple, I'm just going to focus on the simplest cases I can think of. So I still have this sequence E1, E2, E3 of different hypothesis tests, but I'm simply going to assume they're exchangeable with the same type 1 error alpha, the same power beta. And we'll see that Bayes comes in here unavoidably. And if Bayes comes in, we'll assume they have the same prior probability pi naught of the null hypothesis being true. Now this seems very limiting, but there are, but partly I'm just doing it for pedagogical reasons, but there are real reasons where this happens. If you have an industrial assembly line and you do a daily quality control check, the repeated quality control checks involve exchangeable tests satisfying these two conditions. In genome-wide association studies, each test, the alternative hypothesis is the hypothesis that a particular gene is associated with a particular disease, and the null hypothesis is that there is no association. And typically in GWAS studies, these two things are assumed. All the tests are assumed to be exchangeable with the same alpha, beta, and the same pi naught. So I mean, there are important situations where these are satisfied, even though my point here is to mainly view them pedagogically. I'll point out in a minute that involvement of pi 0 is usually unavoidable if you want to be empirical frequentist. That's okay in these scenarios I mentioned, because often pi 0 is known or can be estimated. In quality control, historical records provide the probability that pi naught, that the assembly line is operating correctly. The prior probability of gene disease association is often specified biologically or can be estimated from data. More generally, in exchangeable multiple testing scenarios, as discussed in Efren's book of 2012, you can learn pi naught as the number of tests grows. Finally, when pi naught is not known, I'll resort to the old objective Bayesian approach of giving equal hypothesis equal prior probability, setting pi naught equal to 1/2. All right, so here we go. Let's first consider standard hypothesis testing. So again, we're considering exchangeable simple hypothesis. Oh, now I get even more basic. I'm only going to do simple hypothesis tests. I'm going to do tests of in experiment I, I'm testing H naught I, theta I equals theta 0 I, versus the alternative hypothesis that theta I equals theta 1 I. And the rejection regions Ri have type 1 error alpha, power beta. And they all, and the null hypothesis all have the same prior probability, pi naught of being true. Everything I talk about could be done in much more generality, but for a talk and for understanding what's going on, this suffices. Okay, so what would be the empirical frequentist error probability under rejection? There's lots of empirical frequentist things you could consider here. I'm just going to focus on one. The empirical frequentist error probability under rejection. So this is we're only considering rejection. So we'd look at our long sequence of experiments. We'd look at only those that had rejections. So we have the number of rejections. And then we'd be interested in the number of times, excuse me, the number of times the null hypothesis is true when rejecting. That's the error rate. The number of times you're making a mistake divided by the number of times you reject. And just a little easy analysis, there's not much to it, shows that in terms of alpha, type 1 error, beta, power, and pi naught, the prior probability of the null, this thing in the limit becomes pi naught alpha divided by pi naught alpha plus 1 minus pi naught beta. That looks like a Bayesian thing, and it actually is. It's actually the posterior probability of the null hypothesis given that all you know is rejection. So in other words, if you weren't told the data, and you were just told that the data was in the rejection region, then you would compute this posterior probability, and it would be that thing. So if pi naught is known, then you just report this Bayesian thing, and you have clearly satisfied the empirical frequentist principle. If pi naught's not known, you kind of have a problem, because how do you get something that has that average when this average involves pi naught and you don't know pi naught? Curiously, if pi naught is not known and you do the objective Bayesian thing of saying pi naught is equal to 0.5, well, then you have here a 0.5, 0.5, 1 minus 0.5, so all those 0.5s cancel, and you have that this empirical frequentist error rate is alpha over alpha plus beta. Now, if you're in a high-powered experiment, beta is fairly large, alpha is fairly small. Alpha plus beta might be pretty close to 1. So lo and behold, alpha itself is actually then not bad. So if you're willing to kind of make this objective Bayes prior choice and you have a high-powered experiment, alpha is approximately, has approximate empirical frequentist justification as the actual error rate you'll see. That kind of surprised me. For lower power tests, however, alpha can be far from the empirical frequentist error. For instance, in GWAS studies, they say their power is usually about 0.5. And then this thing you want, alpha over alpha plus beta, is closer to 0.09 than the 0.05. So it's 0.05 would be, alpha would be off by like a factor of almost 2. Okay, let's move. Now I haven't talked about multiple testing before, but I'm gonna do it just because. Well, I mentioned multiple testing when we talked about sequential endpoint testing, but I did this computation and I was quite surprised, and so I decided to report it. So here in multiple testing, now this is a bit confusing. So I had this sequence E1, E2, E3, E4 of experiments. Each of them themselves is a multiple test. So E1 consists of performing M independent tests of hypotheses. So E1 has M tests. E2 has M tests. So, I mean, E1 might have been, I do a GWAS study today involving M tests of disease gene associations. E2 might be, I do a GWAS study tomorrow involving M tests of disease gene associations and so forth. Each time I do this multiple test, I do at each of the tests within an EI, I do a type 1 error alpha over M and the Bonferroni correction. Okay. So then the overall type 1 error for each EI, the family-wise error rate, the probability that I haven't made a mistake in any of them, is then alpha, since I've used the Bonferroni correction within each EI. And there's some power beta M. So here I'm looking at, I'm imagining that a family-wise error consideration again. So an error is considered to be made in EI if any of the M tests results in an incorrect rejection. Okay, if even one of my rejections is wrong, I've made an error. So then the natural empirical frequentist quantity to study is, I only focus on the EIs that have at least one rejection, because otherwise I can't have made a mistake. And then I look at the number of those that have at least one incorrect rejection. And then I take the limit as n goes to infinity. And you can do it. It's not a hard probability computation. You get an expression for this empirical frequentist error rate in terms of all the relevant issues of things up here. If M is large, you can show, if the number of independent tests within each I is large, you can show that this mess here is approximately pi naught alpha. Pi naught is less than or equal to 1, so this is less than or equal to alpha. So very curiously, if you're doing multiple testing with large M and you report alpha, you can say it has empirical frequentist justification. Now, if you knew pi naught, you could say, if you knew that pi naught was a 10th, you could say my empirical frequentist error rate is alpha over 10. You don't have to report alpha. Alpha is just the procedural frequentist error rate. So this is the one example I ran across where the empirical frequentist error rate, which is the thing you want to have, is actually smaller than the procedural frequentist error rate. I thought that was quite curious. Now for sequential endpoint testing, just doing the same thing, you get a different expression. This expression did not have any any useful upper bound, any useful upper bound on it. But I could find a lower bound. I computed the minimum of this expression over beta. And so this thing, the thing you want, the empirical frequentist error rate that you want, is always bigger than 4 pi naught alpha over 1 plus pi naught alpha squared. And if you plug in here like pi naught equal 1/2 and alpha small, this is approximately 2 alpha. So the empirical frequentist error rate of the sequential endpoint testing is at least twice the nominal error rate. And because this is an inequality, it can be much bigger. So this is what I was setting out to show, is that, all right, from procedural frequentist perspective, sequential endpoint testing looks okay. But if you look at it from an empirical frequentist perspective, which I think is the right one, it doesn't look okay. So people should quit using it. Let's see. I guess I can keep going a little bit more. Now I'm going to talk about testing with data-dependent error probabilities. Same setup, exchangeable simple hypothesis testing, testing point null versus point alternative, type 1 error alpha, power beta, pi naught prior probability of the null. But now we're going to be working with data-dependent, before I call them alpha I of xi. But instead of the data, it's convenient to work with the p-values. I mean, usually you can replace xi by, I mean, pi is a statistic. And so I'm going to look at pi here as a statistic, not as a p-value. And replace xi by the statistic pi. So I'll write alpha I of pi as the data-dependent error probability. So don't think of it as a p-value, just think of it as a statistic. Now, first of all, what's the empirical frequentist behavior we would like? If pi naught is known, the target is still the empirical frequentist error probability, pi naught alpha over pi naught alpha plus 1 minus pi naught beta. And if I'm reporting as my error alpha I of pi, then I would want the average of these to equal that. And this average is over the rejections. So n star is the number of rejections. So this is what I want. I want to find error probabilities that depend on the data, and they're empirical frequentist if their average approaches this quantity. I'm assuming exchangeability of the hypothesis, so let F1 of P denote the density of the PI under H1I. And here there's a simple little lemma here, which says that this average of what you report can be given by this integral. The integral of, and I'm assuming that the alpha I of pi is some function alpha of pi. It's not, you don't change with each pi, it's just some, which again in exchangeability you do. So it's just given by this integral in terms of the density F1 of P under the alternative alpha, beta, and pi naught. Now, it's immediate that if I report this quantity, which is the posterior probability of the null hypothesis given the data, pi naught over pi naught plus 1 minus pi naught F1 of P. That doesn't look like a posterior probability, but one of the reasons for basing things on the p-value is that the p-value has a uniform density under the null hypothesis. So this is really pi naught times 1, where 1 is the uniform density under the null hypothesis. And it's easy to show that if you plug this in here, you'll get back exactly the posterior probability of the null hypothesis. Sorry, you'll get back exactly pi naught alpha over pi naught alpha plus 1 minus pi naught beta. So if you know pi naught, reporting the posterior probability of the null hypothesis has exact empirical frequentist justification. And of course, it's also much superior to reporting the thing here, depending on the rejection region, because you have data dependence. And these numbers will be decreasing as the p-value decreases, whereas pi naught alpha over pi naught alpha plus 1 minus pi naught beta doesn't. So this is just saying if you happen to know pi naught, and you happen to know F1 of pi, reporting the Bayesian posterior probabilities has the perfect empirical frequentist justification. So this last bit, and here I'm going to skip this slide because I have to be done in 2 minutes. Using the default choice when pi naught is unknown, I'm just going to hop to this last slide, and don't read this. I just set this up in a particular hypothesis test, and I compared the empirical frequentist performance for 4 different procedures. First, the truth here, the true empirical frequentist average is given in the last column for 4 different sample sizes. Then here I'm saying, what if you report the p-value itself as the actual error? Okay. The second one here, this is the Bayesian answer that depends on knowing F1 of pi. It depends on knowing the alternative density of pi. And then here there's been a lot of talk of minus EP log p as a way to correct a p-value. And this is the error probability version of minus EP log p. Anyway, what do you see? You see that the p-value dramatically underestimates the actual empirical error. Dramatically underestimates, just really bad. Even multiplying the p-value by 2, which gave you a procedural frequentist thing, is still really bad. The minus EP log p correction, not bad. I mean, it gets pretty close to the truth, but it doesn't quite have the empirical Bayes accuracy which the true Bayesian procedure does. All right, there's some references, and I'm done. Thank you.
Thank you, Jim. Feels kind of lonely to be uploading all by myself here. Anyway, all right, we need to move on. I'm going to ask the audience to use the Q&A panel in order to ask their questions. And so Jim can actually start looking at them and maybe answering them. In the meantime, it's a pleasure to introduce Luis Raul Pericchi from the University of Puerto Rico as the first discussant. And Pericchi, you have 12 minutes to do your discussion.
Okay, thank you. Can you see, Bruno, the slides?
Yes, yes.
Okay, thank you very much. Thank you very much for the invitation to discuss this paper by Jim. As he mentioned, I really like the paper and try to convince him to talk about it. Now, one of the things that I'm not going to talk about the whole thing, of course. I don't have the time, and Igor, of course, might focus something else. But one of the things that attract me about these ideas is the possibility of a convergence of the schools of statistics. And of course, we have a long tradition of a Bayesian classification, perhaps starting with I.J. Good. But much less we have had, and this conference helped us in classifying frequentism. And not all the frequentisms are equivalent. Some of them are much more interesting than others. And so one of the best kinds of frequency theories is what you call empirical frequency EF, which is very appealing because the proof of the pudding is in the eating, as they say. And there is a clear link with Bayesian thinking and perhaps also useful guidance for Bayesian developments in a suitable framework. As you saw, many of the properties that Jim was talking about has this punchline, assuming that pi naught is known. Well, the point is that pi naught, there is a lot of information on pi naught, and we can dig it out. We can discover that. We can study that, and actually put that into perspective. So, in a way, he might advance and discover a general standard for most, if not all, of statistics to discuss. And that standard might be agreeable to most statisticians. And that is, the empirical frequentist principle seems compelling to most statisticians. No, having something in which we all agree, is a huge help in making the discussions and the advantages and disadvantages of different methods much more enlightening. Now, the rest of my comments are going to be focused mainly on hypothesis testing, because as you saw, hypothesis testing was the area or the aspect, the facet on which several of these frequencies or procedural frequencies and so on fail. And perhaps the best indication of the crisis of the bad versions of frequentism is the reaction against the wrong interpretation of p-values. And it is not empirical frequencies the correct interpretation of p-values, as Jim gave several examples. And particularly with respect to that reaction, finally, we can say that the world of statistics is changing, and changing in a big way. Now, why is it changing? Well, it's not due to mathematics, I think. It's neither because the compelling reasons that most of us have had in the past to actually become basis. Completeness, Wall's theorem of decision theory, obedience of the likelihood principle, conditional and superior inference, Stein paradox, and so on and so forth. No, it's not because of that, in my opinion. It's because of the science. It's because of why most published research findings are false. The famous empirical frequentist apothegm coined by Ioannidis. That is what really made the current interpretation, or the traditional interpretation, the wrong interpretation of p-value to crumble. Now, also, I want to focus on the last minutes on the importance of the prior. This formula appears again and again in the talk, and you see that lots of statistics, is not most, is just focused and concentrated in power, how to achieve power, how to have power in the problems, and so on. And this is this beta that we have here. But in order to have this principle, we have this guess here, which is pi zero. And if we do several experiments with changing pi zero and changing power, we can see that these averages and rates are even more dependent on pi zero than on beta. So in a sense, it's so surprising that what actually is most important in achieving this empirical frequentist property is somehow left behind most studies. So I then emphasize here that need to baseline pi zero, or if you can wish, talk to that need to baselines, really, which is so important, and we actually can learn about those if we do the correct experiments and studies. And here there's a graph that actually shows what I was talking about. This is a graph in which I change pi naught and I change power. And I change power to 0.5, 0.5 and 0.9, a lot, and change here the pi naught between 0 and 1. And you can see the enormous importance of pi naught and relatively less importance on the power. Now, again, if pi naught is known, but even if it's not known, you don't necessarily have to resort to go to the balance pi zero equal a half, because you can organize, you can design surveys to find out what in some areas it's done regularly, like in epidemiology, to find out prevalences, which is essential. But in other areas, and for example, what is the proportion of the tests that actually end up being wrong or correct is something that can be studied in an interesting meta-analysis. So if, for example, here we follow Jim and Berger and Mosman and Berger approach, for example, about this, and we make a study about pi naught, a small study which we have n data points and we have s equal 90. So again, pi naught is 0.9. But given that this small study, then FDR is no longer a number; it's a random variable because we don't know pi naught. But we have information about pi naught. And that information about pi naught, we can plug at that in that formula and then make inference about FDR as a random variable. And again, the mean is going to be where we saw about 0.333, but we also know that this, because we don't know pi naught, has dispersion. And this dispersion has to be taken into account. And in this case, for example, an interval would be between 0.23 and 0.53, which is rather a large interval because the study was quite small. To finish off, p-values are just too familiar and useful to ditch, quoting David Halter. That doesn't mean that the fact that p-values actually do not obey the empirical frequencies, that means that we have to ditch it. We have to forget about them. Of course, they give information, and then there is this very useful lower bound minus EP log p that is simple, and as a lower bound, it lacks strict empirical frequency justifications, as is pointed out by Jim in the top. However, this lower bound, and that's an experience that I think it would be quite useful to follow up, can be corrected in order to make it closer to a base factor, and then you can show that if you correct this lower bound by a function of n, which is the square root of n over log n essentially, and some constants in here, then it becomes a very reasonable approximation of a base factor, only depending on the p-value and on the sample size. And I conjecture that this will be much closer to satisfying the empirical frequencies principle. I'm going to finish with this quote called "The Future of Statistics, a Bayesian 21st Century." And it's a quote by Dennis Lindley in Advances in Applied Probability in 1975. It had originally been my intention to follow Orwell and use 1984 in the title. But the Finetti 74 suggests 2020. So that is about now for a Bayesian 21st century. So perhaps instead, the direction of growth of statistics for the rest of 21st century will be Bayesian and empirical frequencies. Thank you very much. Some preference.
Thank you, Pericchi. All right. We are starting to have some questions coming in the Q&A. Please keep it going. We will go back to those once we are done with the discussion. And now it's a pleasure to introduce Igor Pruenster from Bocconi University. Igor, all yours.
Okay, thanks very much. Great pleasure to be able to discuss the talk by Jim, even more pleasure since it's the Finetti lecture. And also nice to be able to talk after Luis. So obviously it's a Finetti lecture, so I will have to talk about Finetti. I do it anyway, any talk of mine, and this time I feel I can do a little bit more than usual, so I will quote you a few things of Finetti. I'll talk a little bit about the relation between Finetti and frequencies, which Jim touched upon, and then I will essentially focus on two topics. One is like the focus on observables, which also goes back to Finetti and relates very well to the empirical frequencies principle Jim laid out. And the second stream, so a couple of little stories about that. And the second stream of things I want to talk about is about procedural frequencies principle. And again, I will have a couple of examples about that if time allows, okay? And then I will circle back to the empirical frequencies principle. So Jim said, but Finetti use frequencies arguments all the time. Perfectly true. I agree on that. Okay, but let me just a little bit contextualize in the sense that, so we all know frequentism starts from the notion of frequency and then defines the probability in terms of it. Finetti actually emphasizes and clearly distinguishes between the definition of probability and its evaluation. Okay, so he's very picky on this. And he reverses the frequentist way of reasoning in the sense that the original notion, the primitive notion, is that of probability. Okay, and the link between probability and frequency is not a given. Okay, because it's subjective. That said, it's not that frequentist doesn't enter probability. It rather enters when you have to evaluate probabilities. Okay, so he says that probability calculus, and it's always nice to quote some case of the past, is demonstrating the relation between probability and frequency, okay? But if you postulate such a relationship inside your definition, then it's impossible, okay? So frequencies comes into the game when you evaluate the probability, okay? And he's very clear on that in the sense that, for instance, this quote, he says that everything which can be considered objective, and in particular frequency, has its place, okay? Has its place in his conception of probability, okay? So they match up, okay? It's just a starting point which is different, and the distinction of Finetti, which personally I like a lot, between the definition of probability and an operational point of view, okay? In terms of the evaluation where frequencies comes into the game. And the representation theorem, which Jim skipped his slide, which I saw before about the representation theorem for the 0-1 case. Here I give you the general version because I typically work on based on parametrics, so I like the general version where I have the mixture of IID laws with your Q, your non-parametric prior, which lives on the space of all probability measures. Well, also in this case, you have that at the average of the exchangeable sequences, they will converge to a random probability measure with low Q. And that's in a certain sense, and again, I want to use a little bit of Finetti's own words, that justifies why we expect that frequencies observed in the future will be close to the frequency observed in the past. Okay, so it really connects up the two. But Finetti, and then he took a different path, okay, because the limits, he had problems with the limits, conceptual, foundational, philosophical problems with the limits. And so, again, quoting him, he repeatedly wrote that nothing will ever be known about infinite sequences, okay? So long sequences, yes, but always finite, okay? And that led him then kind of to discard the infinite version of the representation theorem to work essentially with finite additive probability, okay, because he was not happy with that. The limits are something almost metaphysical. That's what he writes in his writing. But still, the representation theorem clearly is the one which best connects in a certain sense. If you think of the average here, with the 0-1 case, it's essentially the proportion of successes, okay, which converts to a random variable, which has then a distribution of prior, okay? So it's the connection between the subjective approach and the frequency, okay? Good, another thing which Finetti emphasized a lot and which also Jim picked up is the focus on observable quantities. And I want to focus on observable quantities based on parametrics because there has been clearly a recent trend, how much recent, I don't know, I would say like 20 years now, moving away from defining non-parametric priors themselves to rather modeling observable quantities. Okay, so in the Bayesian community, in the probabilistic community, concepts like random partitions, which is a marginal property in terms of the observables, or the exchangeable probability partition function, prediction rules, they are now ubiquitous. Okay, this kind of shift from, the Ferguson 73, how do I define a non-parametric prior on the space of all probability measures, to shifting to modeling your observables, and then go back, obviously, to your prior distribution, analyze the properties, but rather in an instrumental way. So that's not the ultimate goal. The ultimate goal is work on the observables, okay? And that matches very nicely with Jim's empirical frequencies principle, okay? So just to make a couple of little stories and illustrate the thing, let me introduce just a tiny bit of notation. So I have your exchangeable vector x1, xn, the distinct values it generates, okay? Because if it comes from a discrete non-parametric prior, we will have ties. So you have kn distinct observations with corresponding frequencies. And when you study discrete non-parametric priors, the key quantity is always this one, okay? It's the probability of sampling something new given the past, okay? And that's, again, in terms of observables, and very much in agreement with the Finetti, which says prediction is the ultimate goal, okay? Science cannot limit itself to theorize, but must foresee. And this is an example of such type of an approach, okay? If you want to characterize discrete non-parametric priors in terms of predictive structures, right, then you can characterize it in, say, 3 classes. So the first one is the simplest case, and it's not a coincidence, which coincides with the Dirichlet process. When you say that that key quantity, the probability of sampling something new, depends on the sample and on the model parameters, but not, and where do the frequency enter? The frequency do not enter, okay? They enter then in the whole prediction rule, but not in the probability of sampling something new, okay? Then the simplest case, you have the Dirichlet. Then the intermediate case, you have the Gibbs-type priors, which I have been working for almost the last 15 years, and now they start becoming finally popular. It's an intermediate case where the probability of sampling something new depends on the sample size, on the distinct values in your sample, and on the model parameters. And you kind of disregard the frequencies. Okay, so that's kind of an approach to subjectively specify the learning structure, and then you can validate it via an empirical frequencies principle. Think about, for instance, thesis sampling problems where you have to predict the number of new genes in a genomic library, for instance. Okay, there you can then do a kind of a frequencies validation. Other example, okay, and again, working on observables, this change of attitude from the things which are back in the Finetti measure in your non-parametric prior distribution more to observables. So if I work with partial exchangeability, nothing else, then you have 2 sequences and exchangeability holds within each of the 2. Okay, so for instance, you have the homogeneity within each sample, you see here, that it's invariant if you switch the order, but obviously not across, but they are still dependent, okay? And what happens, obviously, the Finetti representation theorem holds in this case as well. And the difference is now you're kind of back to square one, like Ferguson 73, have to define the Dirichlet process. Now we have to define a vector of random probability methods. And the traditional approach was, yeah, work out a possible law, which is tractable, for instance, popular structure, additive, hierarchical, nested structure, and then work out the properties. If you change, again, also in this case, your perspective, and you work in terms of observables, then you realize, okay, I look at the observable partial exchangeable sequences, then you realize that most existing non-parametric priors, the Q which have been constructed in this way up here, okay, the traditional approach, they induce non-negative correlation among observables, okay? But that's not the case if you can work it out analytically. Partial exchangeability does allow for negative correlation, okay? And so it's important. If you look at the observables, you realize that you have to be much broader in terms of modeling, right? And for instance, a thing which we have achieved recently, and I mean, you could watch the video of Beatrice Franzolini, being able to build a non-parametric prior which allows both positive and negative correlation between observables. And in that case, it's obvious that if I have 2 sequences of negatively correlated observations in terms of empirical validation of the empirical frequencies principle, I win all the time against the other models. Okay, so that's another story, no? Of why focusing on observables and the empirical frequencies principle. Bruno, how much time do we have now? Couple of minutes, 3 minutes?
You have a couple of minutes, yeah.
Okay. Then I have some thoughts on the procedural frequencies principle. I go very quickly here. I have one model which is nowadays very popular in for instance, in networks or mixtures of finite mixtures, which at the end of the day are nothing else than mixtures of Gibbs-type priors. is this model of Gnedin, which essentially is a finite mixture of symmetric Dirichlet distribution with a certain prior distribution of the number of clusters. Okay? That converges, the number of clusters in this case would converge to a finite number, random but finite, with infinite means. Has a nice predictive structure, which is the reason of its popularity. I don't go into details now. But okay, then let's look at the frequencies properties. Okay, so now I play the procedural frequencies, and I say, what happens if the data are not exchangeable but IID from some P0? Does the posterior accumulate in P0? And here you have a very peculiar inconsistency result. Okay, the Q is inconsistent, but not just inconsistent. You have that your posterior goes and concentrates on your prior guess, so you don't learn anything at all. That, when does it happen? When P0 is diffuse. Okay, when P0 is discrete, you have consistency. Okay, and that's what the procedural frequency test in this case. I would like to play the modern Bayes, and then what I say then? I say that the procedural frequency studies improve my understanding. Okay, I don't discard it. I don't buy in totally, but I say it improves my understanding in the sense that a discrete model is designed, is never ideal for, should never be used for modeling data from diffuse distribution. Why that? Because a discrete non-parametric prior will always generate ties with positive probability. And then you're using that for modeling something which generates ties with probability 0. Doesn't work, okay? And to me, they are not good or bad priors, but rather models which are suitable, designed for a certain phenomenon and not for others. Okay, and that's kind of the take-home message I want to give, right? That's what we have to learn. We have to understand even procedural frequencies things are very useful. Last thing I want to say, and this is really my last slide. Another thing about infinite mixtures. Okay, infinite mixture, one of the most popular based on parametric approaches. Okay, so you have your normal kernel, and you place your Dirichlet prior on the latent level, okay? And what is typically done is that the distribution of Kn, the number of distinct values, in this case, plays the role of the number of clusters. Again, I play the procedural frequencies, density estimation, great in terms of consistency, rates, adaptation, whatever you want, okay? Clustering, to me, totally unsurprisingly inconsistent, okay? Why? Because at the end of the day, you always can't fit a distribution with more components than needed. So in that sense, it's a big buzz nowadays about the inconsistency on the number of clusters. But that's rather a lack of identifiability than a lack of inconsistency, at least to me. Think a little bit about it. You have the posterior of Kn, which is always bounded by n, okay? The number of your sample size. Okay, so there's no changes with n. So a little bit, it's like you have two football teams which play on a soccer field, okay? And then I want to say, I'm interested that my team wins on that soccer field, but then what I'm doing then is I just take the bounds of the soccer field away, and I say, now I want to see who wins without bounds. That's kind of not fair, okay? I'm interested in that particular soccer field. So with the bounds, I'm interested for the fixed n, not letting n diverge. And in this case, actually a good idea, maybe a good idea. An idea I had reading Jim's paper and slides is that actually in this case, an empirical frequency principle would be actually much more fair. You essentially evaluate the mixture model on differing real problems, each with its own fixed sample size, say Ni, and use, for instance, credible sets. And then you compare the actual and reported accuracy as n diverges. So it's essentially like if my football team now plays on many different fields, but always within bounds. And that's kind of a fair thing, because we all know that infinite mixtures for a fixed n typically work well. Okay, that's what I wanted to say. And thanks, Jim, for the wonderful Finetti lecture. Thank you.
Thank you, Igor. So we have basically about 7 minutes because we need to finish at 1/2 the hour. Let's get back to Jim. Jim, the floor is yours. There are 3 questions that have been posted. Yeah, and of course there is the discussion.
Right. Yes. Let me first respond briefly to Luis and Igor, and then I'll go through the questions. Yeah, I'm very glad, Luis. I sort of wrote down for hypothesis testing. I wrote down the empirical frequentist thing involving alpha, pi naught, and beta. then I forgot to talk about how pi naught is the most important thing. If you really want to be in have good empirical frequentist performance in testing, you have to focus on pi naught, and so I'm very glad that Luis brought that out. It's even more important than beta. And I look forward to seeing if his correction to minus EP log P has better empirical frequentist properties, because that's I think a very good way to compare these various alternatives to P values that have been presented. How do they do according to empirical frequentist property? It was wonderful to hear from Igor that working with observables is now completely in vogue. That's great. And I loved his examples of consistency and inconsistency, and agree that, yeah, those procedural, that particular procedural frequentist property is important. I tend to think the empirical frequentist properties are more important, but some of the procedural ones are, and it would be nice to kind of have a list of which ones are useful and which ones aren't. Let's see the questions here. Let me. So here's a question. Does everyone see this question from Terence Savitsky or not?
Yeah, everybody's supposed to see them. Yeah.
Oh, okay.
No, I think just the panelists.
Oh, just the panelists? Well,
Oh,
maybe
just okay.
If I hit answer live, then maybe everyone can see them.
Exactly.
Okay, so now everyone can see them. So Terence Savitsky asks, do frequentists embrace EF? That's the empirical frequentist property, or the more common PF? I think they certainly embrace the more common PF. I mean, when I talk to them about EF, they're all a little puzzled usually. Some of them certainly understand and embrace EF, but it's not I normally get puzzled looks when I introduce EF, even though Neyman was, like I said, very strong on EF. Is EF crafted as a conceptualization of frequentism from a Bayesian experimental setup? It could be, but not necessarily. EF is crafted, I think, completely independent of statistical philosophy. It's just evaluating performance, and it doesn't matter. So I think it's independent of statistical philosophy, and Luis talked about that's maybe one thing we can all agree on, and I think it's precisely because EF is independent. EF is a principle that's independent of statistical philosophy. That means it is potentially something we could all agree on. Brunero Liceo asks, the empirical frequentist principle considers limits of sequence of different experiments with different parameter values without explicitly stating a probabilistic law. Should not we need a Bayesian argument there? Well, again, I want the empirical frequentist principle to just be completely general, not based on any probabilistic laws, not based on any viewpoint. In actual implementation, in any context, you kind of have to choose how you want to do it. You know, so like I mentioned, there could be kind of like a regular frequentist interpretation. There could be an empirical Bayes interpretation, but it's context dependent how you want to apply it. The principle itself, I think, is completely independent of everything. And Brunero is again reinforcing Luis's statement that the most important part of the empirical frequentist principle applied to testing is how important pi zero is. Yeah, can't agree more. An anonymous attendee, that's a strange name, regarding Bayesian attitudes towards an empirical frequentist principle, rather than speaking and thinking in terms of good frequentist properties of Bayesian procedures and unrealistic infinite limits, isn't this just a case of Bayesians naturally wanting any of their probabilistic commitments to be reasonably well calibrated in practice? Yes, exactly. You just, I mean, you do limits to, and I mean, De Finetti did limits too, but he as Igor mentioned, he emphasized he's only doing limits because he wants to know what happens in practice for large numbers, you know, but finite numbers. And indeed, infinite limits are only because of that. You want to, reality is a finite thing. You want to know if you're dealing with a large number of experiments, a large number of evaluations, what's happening. And you go to the limit to see it. So it's just a mathematical convenience. But I don't really believe in limits as anything other than an approximation to large finite reality. And indeed, the empirical frequentist principle is just saying everybody, Bayesians, frequentists, anybody, should simply want their probabilistic commitments to be reasonably well calibrated. That's all it says.
I have been told that this session is programmed to finish right now, and that is how things work. So thank you to Jim, thank you to Luis, and thank you to Igor, and thank you to all that attended. Another round of applause. And well, hopefully see you in person in the next ISBA. Bye.
Thanks, Bruno. Thanks, Jim. Thanks, Luis.
Thank you all.
Bye. Thank you.
Bye-bye.